Alrighty. Last class before the reading week, but I think it's very important for us to know where we are. We are kind of about halfway in terms of the material, but the more interesting stuff will still be coming after the reading week, I guarantee. But just come to the class, just enjoy the lecture, as usual. I just want to go over with you some reminders very quickly. But it really has to do with the semester calendar. So let's go over that together. If you go to semester calendar here, and of course, assignment number 1, since we release 1 week late, so it's going to be due also 1 week late. I believe it's going to be the 16th of June, so next Monday, right? Just make sure to submit your best attempt for assignment number 1, and then I'll also give you guys some solution and also some self-grading criteria. So maybe try to do some self-evaluation to see where you are for that particular assignments. You can reach out to me, maybe in the office hour, if you want to discuss the actual solution. We can do that too. And please know that on Monday, I'm also going to release your assignment number 2. So I would say this arguably would be the most important assignment for the semester, given the following reason. Assignment number 2 is more like a mini project that you're going to do. So for that one there, as part of it, if you really want to get ahead about the preparation, I can give you some suggestion. So assignment number 2 is going to be about, number 1, studying the Antler 4 parser generator tutorial. It's going to be a series of video. You got to watch every one of them, take notes, and make sure you really can reproduce the projects, etc. Right? Well, I'll give you detailed instruction later once assignment number 2 is released. But it doesn't really hurt if you start the tutorial videos maybe just from tomorrow over the weekend, right? Or you can just wait for my instruction on Monday. It's up to you. Okay. But assignment number 2 is also going to be released on the 16th of June, which will be Monday. And guys, don't forget the math review slides, which will be covered in your written test and exam. You may also want to catch up with that as well. And let's go back to the calendar. A little bit more to say. And on the 23rd, which will be the Monday after the reading week, I will release the instruction for your projects. It's going to be divided into different milestones. So you will see milestone number 1, milestone number 2, that's going to be due. I'll speak more about it in the instruction. Also, I'll make sure on the 24th, our first class back from the reading week, I'm also going to talk about your project specifically, just give you some idea. And your safest bet will be to find your teammates if you haven't found one yet. It's going to be either a team of 2 or a team of 3. Not 1, also not 4. All right, so it's going to be 2 or 3. Please find your teammates if you can. And of course, I'm also going to try to help you guys. If you cannot really find a teammate, I'll try to see if there's anything I can do, maybe over the e-class or maybe try to be the mediator, to assign you teammates, right? All right, so project is going to be released there. And you want to also get very cautious about your programming test, okay? It's going to be on the 3rd of July, which is going to be a Thursday, right? So on the 1st of July, you can see that on that particular Tuesday, we don't have a lecture, right? It's a national holiday, so we won't be here. I'm thinking about to arrange maybe a mock-up test, maybe for you guys, so you can maybe give a try to see how the lab test is going to be like. I'm pretty sure since you're in the 4th year, right, or 3rd year, I'm pretty sure you have taken some lab tests before, but it's good to give you some mock-up tests. I can definitely do that. I think it might be nice to maybe have it. I can maybe do some survey to see which one you guys prefer. It's better be Tuesday or Thursday. I think maybe right after our class, maybe about 7 p.m. I'm happy to stay for 1 more hour, so you guys can take maybe a 10 minutes break after the lecture, and then we can all move to some lab space. I'll try to reserve the room, and then it can be maybe from 7:15-ish to 8:15, like 1 hour, so you can get some idea. I will also make the mock-up test material available to you after the mock-up test, right? I think that can be beneficial for you. Anyway, I'll keep you posted. So the programming test over here is going to be completely based on what you're going to do in assignment number 2 about the Antler 4 tutorial. So that's why I said, arguably, your assignment number 2 is going to be the most important one. It's going to impact your programming test. It's also going to impact your project as well. All right. And then, of course, your written test is going to come almost the last few weeks, but also just keep up with the material in the lecture. So by then, July 17, we should be able to dive deep into one of the parsing algorithm, which is going to be very important, right? So we're going to spend quite a bit of time in the syntactic analysis. And then also we're going to do a little bit of design patterns as well. I'll keep it, we'll see how that goes. And as for the exam, I should be able to know about the dates. I think you guys will find out the same day as me. It's going to be somewhere between August 7 and August 14. I don't know which day. Don't know yet. So please don't make any travel plans. All right. So make sure you're available for that exam period. It's going to be a 3-hour exam, in person, paper and pen. And I'll give you more information a little bit later. All right. Any question about the course? All right, guys. As I said, kind of in the beginning of the course, we are kind of relaxed and kind of just focus on learning in the lecture before the reading week. But after the reading week, there's so many things that are going to happen for the course, just the nature of the arrangement. So please watch out for the deadline, right? If you got any concern, I'll be happy to talk. I will have some maybe special office hour. May not be Tuesday, Thursday, the usual time. I will still be on campus, maybe just different time. So I'll let you guys know over the weekend, maybe Sunday, about some special hours. Maybe I'll try to make it some Zoom hour available, since some of you might have to be working during the reading week. I'll see if I can accommodate. Okay, we'll see. If no question about the course, all right, let's now talk about recap. Okay. So today we'll finish the lexical analysis by kind of synthesizing what we have talked about so far to see how the scanner can look like, and then we'll move on to syntactic analysis. We'll just do a little bit introduction, some example. We'll do the more serious stuff after the reading week. One more thing, I would suggest you guys can also, if you want to do a little bit pre-study, this can be beneficial for the final exam. Okay, there's going to be a lecture. Okay, some pre-study. Okay, I'll put it here. There is some pre-study you can definitely give a try about what you learned back in 2030 about polymorphism and dynamic binding. The reason being, I'm going to give you guys a lecture, possibly the second week after the reading week, when you are diving deep into the project and also the programming test. So there is a design pattern that Antler 4 actually used very heavily, which is called the composite and also visitor design patterns. That's going to be made use of by Antler 4. So think about what you learned back in 2030 about polymorphism, dynamic binding will be the prerequisite for understanding these two. So when I give you guys the lecture after the reading week, I will assume some very basic knowledge about it. I may not be able to go from scratch, so you can definitely catch up with brush up these topics. I'll try to give you guys maybe some lecture recording from my 2030, so you can consider. Otherwise, if you go back to your material from other instructor, that's totally fine. The principles are really the same. So I'll leave the choice to you. But you should really know very well about polymorphism, dynamic binding, before coming to this lecture after the reading week. Okay, that'll be my suggestion. And of course, polymorphism, dynamic binding will also be covered in your written test and exam. Okay. Okay, good. Let's now do some recap from last time, and then we'll continue. So last time we really, again, we dived very deep into the, first this one here. Yeah, just remember when you study for translating from regular expression into epsilon NFA. So we talk about how to really draw the diagram. That's a correction from before, right? You can look at the recording for the exact correction, right? It's really about this concatenation. I was correcting myself over there. And then we talk about the formulation of the extended subset construction. Extended in the sense that we have to handle epsilon transition by calculating the epsilon closure. And when we are doing the epsilon NFA into DFA conversion, we have to use this technique. And these equations over here that we kind of went over one by one is about the formulation of the process, right? So I would suggest when you study about this particular formulation here, take a look at each equation here and see the correspondence in the table over here. That's the table of the example we did in class. So you want to see the correspondence between the two. All right. So that would be a very nice way to synthesize about what we learned from epsilon NFA and how to convert that into NFA by removing epsilon and also non-determinism. All right, so that's something we basically focused the whole class on Tuesday, which is worth it, about minimizing DFA. So we dive very deep into the actual coding for the algorithm. And, oh, by the way, minimizing DFA is not really required for your assignment number 1. So you don't really need to do it. But if you're really interested, feel free to actually implement this algorithm to extend your assignment number 1 for your own interest. Okay, it's completely up to you. But the most important function that you have to understand about this minimizing DFA algorithm is the splittable over here, right? I think your fellow student kind of asked me during the break on Tuesday, which is a very, very good question. These two conditions are both necessary in order for a partition to be split out certain splittable subset. All right. Number 1 is to say the splittable subset cannot be the entire P. So we don't really have this subset relation. Equality here is excluded. So it's got to be a proper subset, cannot be the entire one. Okay, I'll give you a little bit more example when I recap. And the second one here is to say, which I think this diagram here, if you now revisit this, it actually kind of helps. From the current partition here, if somehow I can find some proper subset S, and then by doing the same transition using the same character, I can go to the same partition. In that way, I know that I can split this S out. Again, it has to be maximum. Okay, look at that. There's a keyword here, maximum. You cannot just selective say, I just want to split one state only. No, you got to choose a maximum. So if you review the example that we did last time, it's got to be number 1, maximum, and number 2, it's got to be proper subset. Number 3, it should really lead to the same partition that's actually different from the original partition, right? Try to review all these points when you study for the algorithm. Okay. And the example that we did over here, that's just about partition. Was this, we got initial one. The initial configuration is always 2 partitions. You got the accepting states, and also you got the non-accepting states right here. Okay. And one question I was asked was something like this. Let's say we're here. And then we have to revisit every partition, 1, 2, and 3, to see if we can split anything further. The question goes like this. In this particular case, we can see that from S2, S4, they will lead us both to a different partition, which is green. So why are we not splitting S2 and S4 out? Because when you actually look at number 3 here, I said the only one we split out is only S1. But S2, S4 remain to be blue, right? So the short answer is, even though S2, S4 here lead to the same distinct partition, so that will definitely satisfy this condition here, right? It actually lead to a different partition here. However, it does not satisfy the proper subset notation, all right? Meaning that S2, S4 itself is not a proper subset of S2, S4. In that way, you cannot split the entire set out. Also, your fellow student asked me, is it okay if I only split out S2? Let's say I will make S2 maybe let's say brown, and then I'll keep S4 blue. Also, you cannot do it because, as I said, it has to be maximum. You cannot selectively say I only want to split one set, but not 2, right? Got to be maximum. Got to be maximum, and the maximum set here has to be a proper subset. Otherwise, it cannot be split. Okay, very important insight. Right, 1, 2, 3, 4. I'm going to do one more tracing table together with you for you to get a little bit more idea if you want to maybe redo this example here. And there are another 2 examples you will see on the slides. This will be the second example. Oh, sorry, just before I get there. So once you got a final partition here, that means no more optimization can be done. You basically reach a fixed point for the while loop. So that's how you actually redraw the DFA. That's actually minimized in terms of its states. And for that particular example, we said we got about 30% reduction, right? You can try to calculate the similar statistics maybe when you do the other 2 examples. Okay? So please make sure you know how to do this, how you can reconstruct the DFA according to the final partition we have. This really is the final outcome we will need, which is a DFA with minimized number of states. And example number 2 for you to exercise, and example number 3 as well. During the reading week, I will also post a solution on the lecture side, so you can also compare. All right. Okay. And I want to do one more thing, just before we dive into the final stage for the lexical analysis lecture. I want to give you a little bit idea about how to trace. Okay. So you can see that we got number 1, number 2, number 3, number 4, etc. Right? Okay. Now I want to show to you how you can trace this. I'm just going to write it down. Okay, to give you some idea. Okay, I'll put it there. That's a new stuff for today. Okay, I would say tracing the minimizing DFA algorithm. So I'm going to use a table. I will only do part of it, and then you can feel free to actually do a little bit more on your own. Okay, let me just go directly to the table. Okay. So let's say we got a table here. I'm going to put 3 columns there. Okay. Okay. And then column number 1 is going to be about the capital P, all the partitions we're considering, capital P. Okay. And according to our annotation, you can refer back, it will be the refined partition so far. That's what we have done so far. Can we do any further? We don't know. Refine partitions so far. Okay, that's 1. And then I'm going to do another set over here. Let's call that T. All right, so this is the last refined partition. Last refined. Basically, P and T, if they are different, that means there's still some scope for us to do maybe another try to see if there's anything further. But if P and T just happen to be the same, that means we have already the T here that we try cannot do any further improvement from P. That means we're done. Right? That's guarantees. The algorithm is going to terminate at some point. Okay. P equals T means no further optimization possible. Okay, that's something you can also refer to. All right, and the final column I would like to trace is the S, which is the subset I can split out from P. So this will be maximum splittable subset, proper subset, how about that? Proper subset of states. Notice that there are many terms over here you got to watch out for. For example, number 1, we'll talk about maximum. Maximum, also got to be splittable, and also it's got to be a proper subset, right? So all these are important, right? Just watch out for that. All right, let's talk about how we start with. So I'm not going to refer to what we did on Tuesday. I'm just going to quote the result over here so you can see how things can go on. Right? You can see it just provides you with another kind of angle to see how things work. Okay, so what we start with is like this. Let's say we start with this initial one. So we got basically only 2 partitions, accepting, non-accepting. So we got non-accepting will be the error states, and also S0 to S4. S1, S2, and also S4. And the accepting state will be S3 and S5. Okay, so just to be consistent with the color, we actually got partition 1, non-accepting, and also partition 2, accepting. Right, that's how we start with. And Before the very first iteration in the beginning, we simply haven't got any refined partition just yet. That will be the goal for that current iteration. So start with empty. And then we haven't found any splittable just yet. That's about to be found. So think about this row over here is the beginning, the start of the first iteration. And then what we're going to do is we're going to, at the end of the first iteration, we're actually going to do step number 1, right? So we're going to do step number 1 right here. All right, so you can think about the 1 here is really about the 1 here, okay? After doing this particular step, we're going to end up in this particular one by splitting S2, S4 out, right? That's exactly what I meant, right? So let's now just put it in the table so you can also try this kind of tracing, just to make it a little bit more programming-like, which some of you might prefer. All right, so for this one here, we're going to get basically the partition, right? So that one there at the end. So here we got, around the end, we are actually going to have SE. And also, well, let me just copy that. We still have, I want to fill in the T and S for you. Okay, so this one here, I can just copy. Okay, right here. And then the T here is something that we're going to change. Okay, but what's the splittable set? The one we did was exactly S2, S4, right? So that's the one that we have figured out. That should be split out, okay? So I'm going to put it there, first of all. So that one there is going to be S2 and S4. Right? Once it is there, so we are just going to, excuse me, see what T is. T will be the new, the last refined partition after S has been discovered. So it's going to be S2, S4, and then, because S2, S4 is taken out, right? So we only got these 3 left. SE, S0, S1. And then we still got S3 and S5. Okay, so think about this one here is the blue one that we just got, the new one. And then we got the pink one, and also we got a green one. They stay the same. All right. Okay, you can think about this one here is the little p. Think about this a little p minus capital S. And of course, this one here is the capital S. Right? Now you can see a little bit better about relation. And this one here, if you want to think about it, it's not splittable for the reason I just explained, right? It's not maximum, right? Yeah, sorry, it's not proper subset. Not splittable. Okay, let me do one more row. Okay, and then I'll give you, and then you should be able to see how you can proceed. So after this, we're just going to result in the P over here being different, right? So what we do is we're just going to have S2 and then S4 will be 1. And SE, S0, S1. And then we got S3 and then S5. Okay? Okay, that'll be the beginning of the second step. So this will be basically what you got to do for the second step. And of course, this one here will be the blue one, and also the pink one, and also the green one, right? Of course, what you can expect to really trace over here will be in number 2, we're actually going to, let me just show you very quickly. In number 2 over there, we're going to discover S1 to be split out, right? That's something you can expect to trace in the table, but I'll let you do that. So let me just fill out that particular row. So now we are in the beginning of the second iteration. We're still going to reset the T and S accordingly. So over here, you go back to the empty over here for T, and also undefined, just to begin with. Of course, they will be set appropriately later. Okay, but it is very important for you to see this. Okay. Okay, good. Well, guys, any question so far? We're good? And another thing you can also see, let me just show to you. If you consider these two sets, let me make it a little bit thicker. If you look at the P here, oh, sorry, the P and T, right? The P here that we start with, and also the T here. You can see that these two are not the same. P is not the same as T. That means more optimization might be possible. That is why we have to go for step number 2 to see if we can somehow reduce this any further. Indeed, we can. So that's why we got 4 steps in total. Right? This table here is going to be quite big, if you try that, but I think it's worth kind of an exercise for you. You can do this for this example here and also for the other 2. I think that's going to help. Okay. Alrighty. If no further question, I want to talk about the last part for the lexical analysis. We'll do that, and then it's going to take a chunk of time, hopefully about 10 to 15 minutes, and then we'll take a short break. After the break, we can start with a new lecture. Okay. Okay, so this is also some exercises worth doing. Okay, so basically, given some regular expression right here, okay, so somehow you want, let's say this, okay, let's say given some regular expression, right? So the actual question here is not really the focus point. I'll just give you one example for regular expression. So let me just give you some idea. So this will be also a very nice way to synthesize what we have done so far. Okay. So let's say you're given some input. Let's say your given input is a regular expression. And the output should be a D of A with the minimum number of states. Right? So that's really the problem pattern we want to talk about, right? Input and output. Now, given what we have learned so far, you know the solution, but let's just review the workflow for you. Okay? Let's start with the input. Let's say you got your regular expression here, which you can specify in the textual form, right? It's going to be textual form. And for example, when you study through the Antler 4 tutorial video, you will see that in order for you to specify different categories, which I'll mention, different category for the token, it could be identifier, it could be maybe keywords, or can be whatever, like a delimiter, right? Different categories. You're going to specify them textually. You don't draw D of A. In Antler 4, you don't do that, right? You just specify textual form. That one there, internally, is going to be turned, first of all, into epsilon N of A, right? And we definitely talk about how to do that visual translation, right? We did that. That's something that's already covered. Once you get an epsilon N of A, you can turn that into D of A. That will be more like an intermediate. So let me just use a different color here. Good. And once you got your epsilon N of A, now you can turn that into D of A. basically by removing two things. You want to remove the epsilon transition. You also want to remove the non-determinism. So what we have over here is something called the extended subset construction. Of course, it's the lazy evaluation version because we don't really have to consider all the possible subset, which would be exponential. Okay? Lazy evaluation, okay, is going to remove two things. Number one, epsilon transition. Number two, non-determinism. Right? Okay, we talk about all these. These will be good reference point, when you review the course material during the study week. Okay, DFA. And this DFA here is not necessarily minimum in terms of its number of states. So that's what we're going to apply what we learned last time. And the final step is really to somehow minimize that. So this will be the final DFA we're going to get. So this part here is going to be minimize Of course, the blue and the pink may be the same. That's okay. Just simply means there's no further optimization we can do, which is totally fine. Luckily, to go, this is the only part you have to specify as a user of Antler 4. Once you have specified this, all these are automated. All right? You don't need to really implement that by yourself, but you should really understand about the theoretical foundation. Okay? So this is, in the context of Antler 4, this one should be manually specified by Antler 4 user, like you guys, right? And then the rest right here will be automatically generated. Okay, this part here. That part there is going to be auto generated. All right? Because the processes in between are well defined, as we talk about. All right? So for your projects, you definitely don't have to implement any of these. You definitely don't have to. But in the written test or exam, you should know the details about these approaches, right? So hopefully that's clear to you. All right, so that's really the good value about this page here. Even though it's only a single exercise, but does synthesize many things you're supposed to know up to this point. All right, let's see the final part about the lexical analysis. Let's do this part here, and then we'll take a short break. Okay, hopefully not too long. We'll see. How do we implement the scanner? Okay. This is a term I kind of briefly mentioned, which is talk about syntactic categories. We got different categories. So let's give some example. It could be some keyword. Let's say if you're defining the, let's say lexer or scanner for Java language, could be the keyword like a while, if, else, new, etc. Right? Or extends, or implements, things like that. Can be identifier, just about if you want to give a name to the class, give a name to the variable, what should be the pattern for the identifier? Also, white spaces as well, which is quite an important category. All right, just about if you want to have different spaces, it can be can be a single white space, it can be a tab, it can be a carriage return, as many as you like. So typically, the white spaces will be ignored by the compiler. You will see that as you go through the tutorial video for Antler 4. Right? So these are the categories. Okay? And then a compiler, the scanner, they must recognize the words from all syntactic categories. Think about each word may have to match one of the DFA you kind of specify. Right? So at a high level, this is what we have. Okay, so thinking this way, right? I will just put it here. So think about your scanner goes like this. So your scanner will be specified as more like a union of different patterns. So it could be R1, regular expression 1, or R2, or all the way to R, let's say N. So first of all, what we have is we got N syntactic categories. And then, of course, the plus sign over here tells us a word satisfying either of them should be considered valid. Okay, so this one here, a word recognized, how about that? Or accepted. Recognized or accepted by either of the patterns is returned as a token. Okay, eventually we're going to return a sequence of tokens into the parser. Return as, sorry about my writing, as a token. Right, so keyword I'm using here is the token, really, right? Token, right? Can be this, can be that, right? Any of them. Each one of them is just a regular expression. Okay, R1 over here is just a regular expression. The regular expression for a particular category. Of tokens. For example, it can be identifier, can be keyword, can be white spaces, etc. Right? So that's kind of the conceptual sketch about what a scanner is. And we're going to see that more or less implemented. I'll give you some example. Okay? We'll see some pseudocode, but that's good enough to have that kind of knowledge. Okay? Okay, and then should be returning one word at a time. If the word actually matches one of the regular expression, it will be returned as a token. And this guy here is also very important. As you study through the pseudocode, the algorithm I'm going to present to you, very simple one, it's going to really try to recognize the longest possible character sequence as a valid token. Not the shortest possible, the longest possible. Okay? That's something you will see. And this is not exactly covered in the slides, but in practice, you can also try to say certain priority may be given to the recognition of the pattern. For example, if you read NEW, right, this might be satisfying both the identifier category and also the keyword category. Which one should be taken, right? In this case, we might say we want to go with the keyword and then identifier, right? I believe in Antler 4, it depends on the order of the pattern you put on the actual file, but you can look into it. Okay, priority. All right, so let's now take a look at some very simple example to put everything together. Okay, just give me one moment. I'll fix something on my end in just a few seconds. There we go. Okay, good. So here we're gonna, let's say we want to match some register names. And let's say the register name is going to start with the letter R by some numbers. Make it simple. So this will be the regular expression, right? We say we got R followed by any of the digits from 0 to 9, at least one of them, right? You can see the plus over here, right? At least one of them. And we got some diagram. I'll redraw it just to show to you. And then, okay, so just understand what the problem is. We're now going to see how the scanner is going to work to actually recognize the regular expression like this. Especially want to put the syntactic category into play. That's what I want to go over with you. Okay. So there is a pseudocode here in page 62 on the slide. I'm going to go over this together with you very quickly, and then that's it. Okay. Okay, right here. Let's see what's really involved over here. Just to start with, you can see that we got something called token type. What's the type of the token? So if the token is simply R, that means a register type. If the character is either 0 or 1 all the way to 9, it's a digit. The EOF, specifying the end of file. You may have seen this word maybe back in 2031, right? Just tell us it's the end of the input, right? It's just called other category. Anything else is also other, okay? So, and then we got transition table. You can think about that one is more like the minimized DFA transition table, which can be done, use if and else. If we are now in state number 0, we read a register category, and then we're going to go to S1 state, right? Like a transition, okay? So we got transition here. So this one presumably will be the delta of some minimized DFA. All right. And then we got token type, similar. Our token type here is simply saying, at the end, we will only recognize the word as a valid token if the type we're getting is simply a register. If we're only getting a digits, it's actually not a registered name, right? We want to make sure we read something like this, R24, for example. If we only read 24, it's considered as a digits, but it's actually not valid. Okay, something like that. Also, this one is telling us, depending on which state we are, we can also decide whether it should be accepting. Okay, so S2 is the accept states. Okay, so S2 over here is the accept states, because all other states are considered as invalid. Accept states right here. All right, and just for your information, I can draw that very quickly, right? Just to show to you. You can double check, when you study for this example here. So what we have is we got the following DFA. We got S0, and then by reading the character R, we go to S1. And then if we read single digits, which can be from 0 to 9, that will lead us to S2, which is accepting. But you can read more digits if you wish. If the name is longer, you can read as many more D as you like. Okay, and we got some error states. Anything else, because it's a DFA, you got to make sure you cover all the input in every state. So here, from S0, if you're reading some digits right away, you cannot start a registered name with the digits or anything other, any other. And then from S1, since you already read R, you cannot read R anymore. Okay, finally, if you have already read at least one digit, you cannot read any R anymore. So R and other. And this one here is going to be any R, D, or other. Right? That's basically the DFA. That's kind of minimized in terms of its number of states. Okay? So we're going to see how exactly this one here can be traced using this algorithm over here. Okay, we're going to see that. I'm kind of reaching the halfway mark. Why don't we take a very short break, taking attendance, and then we'll do this one here very quickly, and then we'll move on to the new lecture. All right, so let's now try to look at this scanner implementation here. Okay, we'll take a look. I'll go over the algorithm very quickly. There are different phases we got to do, but the best way to kind of understand it would be to use a very small example, and then to get some idea. But a detailed study will have to be left to you guys. Okay, but let me know if you got any trouble. Okay. So there will be a call stack I'm going to use over here to trace about the different states. Basically, we're going to go over the input character one by one. Every time we read the input character, we're going to put something onto the stack about the states. And eventually, we have to get to the point that we know that we are reaching the end of the file, of the input. So we want to know whether the final state we are reaching is really an accept state. Sounds very intuitive, but let's just see exactly how that's going to go. Okay, just give you some idea. The example I put here is like a R24 followed by end of file. I think we can just do R2 just to make it even easier, right? We just want you to get an idea. And as an exercise for you guys, you may want to try. How about this one here? I can tell you that this one here, if you see R24 up to here, it is okay, but you got multiply and 3. That one doesn't seem right. But you want to see exactly what's going to happen if you pass this input to this scatter algorithm, right? That will be the exercise for you. Okay, that's a little longer, but it will be more detailed kind of walk through. I'll leave that to you. So what we'll do is, if you don't mind, I'm going to change that to be a little bit simpler. Why don't I say just R2? Okay, very simple. So we basically got R2, which should be a valid name for the register, and then followed by end of file. That's what we'll do. Okay. Let's see what's going to happen here. And we're going to trace several things. We're going to get a word, states, and category. Okay. So let me just highlight a little bit here. So we got, let's say we got the states here. State, a bit thinner. So we got the state here. And also we got a state here. And also we got the state here. And also we got to stay here to be updated. And also we got to stay here. Just stay here. And we got to stay here. And here. And also right here. Right? Of course, apparently state is a very important variable, right? We're going to see exactly how to trace it. So that'll be the states that we're going to see. Exactly how it's going to change. We also got another one which is called a word. The word we are reading. We have read so far. Word here. And also we got the word over here and the word over here. And also, I see that we also got stay here, right? Okay, let's see if we got any more. Okay, we also got stay here to do the transition, of course. And we also got the word. All right, finally, we got category. The category over here is going to be, let's see here, we got category, which is going to be more like a table lookup, which I'll show to you. And also we got, I think that will be it. Okay, good. Okay, so category and etc. All right, let's see how things are going to change accordingly. Okay, initially we got the states being the start states S0. Okay, that makes sense. And the word that we have read so far is epsilon. Okay, just epsilon here. Okay, and then initialize an empty stack, indeed, and push something symbolically called bat. Okay, the bat here wouldn't be so applicable for this particular example, but you will see that when you trace the other one later. Okay, so what I will do is I'm going to put just a bat here. So push that on the stack. So stage number one about initialization, that's it. And then we are just going to say we're going to keep going for stage number two as long as the current state is not an error state. All right? So error state, so S0 is not error state. So now we should really keep going for the first iteration. And the next character over here is going to be the first character to read. So the next character should be R. All right? So right now, the next character here should be R. So the word is going to be epsilon plus the R. right? So we're going to update the word to be just R. And then we're going to say, if the states it's already accepting, but it's not the case because the state right now is S0. As we said, S2 should be the accept states, so we're not accepting just yet. So this one here doesn't apply. And we're going to push the current states, which is S0, onto the stack. So we're going to do S0 right here. And let's now figure out the category. We're going to do some lookup. The category here is going to be, we just find a character, which we know is R, and then go to the table character category, which is right here. Character category R correspond to register. So category will be register. Okay? So category will be register. Okay? Oh, sorry. There we go. Okay, so that one there, you can think about if you match the character R, you will see that one there should be register. Okay, I already updated right here. Okay, register. And then we're going to update the state, which is like a transition, which we did earlier. So how do we update the state? Go to the transition table right here. And then the state right now is S0. Start from here. And then you're going to apply the category as the transition. And the category is register. And the corresponding states should be S1. Right? So that means we should really update the states from S0 to S1. So now it's the new states. Okay? And then we go back to, so that's kind of the end of the while loop. Okay? So now the state has been updated to S1. So we go back to the while loop over here. S1 is still not error state, so keep going for another iteration. And then we're just going to try to see what's the next character, right? The next character should be 2. Okay. So rather than R, it's going to be 2. Okay. So the word is going to be R plus 2, which is going to be R2. All right. And then the state here is now S1, which is not really accepting, right? It's not S2, basically, right? So we go here and push the S1 onto the stack. So what we do is we push the S1 onto the stack. And we got to update the category. So what's a category? So we just get a character, which is now 2. So 2, if you look up the character category here, 2 correspond to digits. So the category is going to be updated to digits. Right here. And the states, let's now try to see. For the state, current state is actually S1. And then we are now applying digits as a category. The corresponding states should be S2. So that means we're going to update from S1 to S2. Right, pretty straightforward, but I just want to show to you what's going to happen at the end very quickly. All right, so now we are actually now done with this, and we go by the while loop. And then you can see that state is still S1, not the error states. So what's the next character? EOF. Okay, that means the end of the file. All we do is, rather than 2, it's going to be EOF. Okay, so the word is now going to be R2 and then EOF. Right? So now it's going to be R2 EOF. All right, that's the word we have read so far. And then the states here is now S2. S2 is indeed accepting. So somehow we have to reset the stack. Just get it empty, right? Well, we'll get it in a moment. So here, because that's already accepting state, we should really reset the stack, and then we should really push the states in there. Okay, we can reset a stack over here. And then we're just going to push this particular state in there, which is S1. Oh, sorry, S2. Beg your pardon, S2. Okay. And then from then onwards, you're just going to update the category and also states accordingly. Okay, and etc. Okay, you can see this kind of a process here. You just want to go over until the end, and then to see if you can reach some accept states. From there, you're going to figure out what's the category for what you have read so far. It turns out the category will just be register because you have already reached S2. So the other stages over here is just going to do some finalization for the algorithm, which I can let you try. But eventually, we're just going to return that it's going to be a register as a token. Okay. That's the part I can ignore just in the class just to save a little bit of time. But for you guys, you should really give it a try to continue with the tracing and see how this can be done properly. Eventually, return R2 as a register. Right? That would be something you want to try. Okay? In the test or in the exam, I may not actually ask you to really trace the whole thing because it will be also very difficult for us to grade as well. But I think you really want to get, at least try to trace maybe this one here totally, and also try this one as well. I might just ask you some sub-step about the algorithm, just to kind of ask you about, oh, if I try the stage number 3, for example, what's going to happen? Things like that, right? You want to get used to about how things are going to work. Okay. But the main message to take from here is, in order to really implement the scanner, you already have some minimized DFA. That's why we kind of lay the theoretical foundation before in the classes, right? Okay. Any question? Yes, please.
So we said eventually the return R2 is a register, and that's because we see from the token type that S2 is the
register. Yeah.
Yeah, register. So that's what's returned.
That's correct. That's correct. And of course, the scanner itself is not going to return just a single token. It's going to read on until the end of the input file. And this one here just incredibly oversimplifying. We just say we only got R2 to be read. But in your actual projects, it's going to be a very long file about your programming language, right? And then you can read all the way to the end. You might generate maybe 100 or 200 tokens. From there, we're going to pass that to the next phase, which will be syntactic analysis. Yeah. All right. All right, very good. If no further question, I would suggest we do a little bit like a 15 minutes or so just to do some introduction to the syntactic analysis. Do a little bit. We can review a little bit about context-free grammar, and then we'll dive deep into it after the reading week. Okay. So that'll be it for the lexical analysis. We're done. And for the syntactic analysis, as you can see, it's kind of a big lecture. You can see we got 96 slides in total. Okay. So what you guys maybe learned back in 2001, the theory of computation course, you learn about context-free grammar, learn about ambiguity in grammar, derivations, things like that. We're going to review them for sure. That'll be only the first 1/3. The second 1/3 is going to be about some parsing algorithm, which we're going to study, which I don't think you have seen before, not even in your 3101. I don't think you would have been taught like a parsing algorithm. It's too kind of specific for like a compiler. So we're going to talk about 2 parsing algorithms. The one of them is called top-down. The other one is called bottom-up. We're going to learn about both of them. It's going to be the entire lecture, but about 1/3 for each. We're going to go over them very carefully. And then in the middle, we're also going to talk about some design pattern as well. So that'll be more or less how the course is going to go. Okay, we'll see. Let's start with an introductory lecture slides, just to review about where we are, in the context. I think that'll be very useful. Okay. So if you recall this diagram over here, oh, sorry, just give me one moment. I'll bring back the diagram on my page. There we go. There we go. Okay. All right, so this diagram here, we saw that back in our introductory lecture. And then you can see that what we have done, was the lexical analysis. That was what we have done. And the scanner, the algorithm we just talked about, is going to give a sequence of tokens, right, for the syntactic analysis, right? So just to remind you, the scanner over here is basically the R1 plus R2 plus all the way to Rn, right? That's something we kind of said about, before the break, right? That's something just to remember. Okay, and it is important also to say the sequence of tokens, each one of them has a category. Each token has a category. For example, register, right? The one we just talked about. Could be register, could be digits, depending on exactly what you want to recognize. And the parser over here, of course, will be something that we have to study in detail, right? So the parser. It's going to take us many lectures to really review and also learn something new about parsing algorithm. Okay? So think about the parser itself. Conceptually, you're basically going to be given a sequence of token. So this will be token 1, token 2, all the way to maybe token n. Okay? Linear sequence of token. Linear in the sense that it could be an array, could be an array list, can be a linked list, doesn't really matter. It's just linear from left to right. Okay, that's what the scanner will give the parser. And the parsing process can either be top-down, parsing, or bottom-up. Either way. We're going to learn both. Okay, it's or. Okay, that one there is going to give you a tree. Non-linear. Non-linear. Abstract syntax tree, which we did mention, right, in the introductory lecture. You can review that lecture there, just to see a little bit more about intuition. And then at this level here, we are no longer focusing on individual characters. We're going to focus on individual tokens. So the focus over here will be tokens rather than characters. However, for the first 1/3, when we kind of review about things like a context-free grammar, so the way, just make the example a little bit easier to digest, the one we put there looks like a character, but it's really a token. But just in case you got confusion, you can always let me know. I can remind you, right? Just remember, we're focused not really to process character by character, but given tokens. Okay. And then to really, and we also got a review. Before that, we're going to review about context-free grammar. And also, given the context-free grammar, how do we do derivation? And also, how do we draw parse trees? We'll do all these three first before we get to the parsing, which will be done computationally, right? We'll do all these. And this part here, we wouldn't say too much about semantic analysis because it really depends on the individual projects. So I think once you guys start with the projects, I can speak a little bit more guidance about how you're supposed to do. Or maybe when I meet with each one of you, each group, I can also give you some guidance because each group might do a little bit differently. Okay, of course there'll be a target program eventually. Okay, one more thing. The only thing, we'll spend more time during the class. Let's use this one here, it's fine. For semantic analysis here, the only thing that we're going to spend more time talking about will be the design pattern. Okay? Design patterns. Composite. And also visitor. Right? We'll talk about it either the first week after the reading week or maybe the second week, the latest. Okay? Because once you kind of see the Antler 4, you will see that somehow they will tell you that they use a visitor pattern, but I gotta also talk about what exactly it is. You may not have learned that so far. Even if you have, you may have forgotten about the details, right? That's something we'll do. All right. 10 minutes, why don't we see some example, okay? So that's about the parser in the context, and then let's now talk about some example here, and we can also review the terms that we learned, that you guys learned earlier in 2001. Okay, let me just see my notes over here. Let's take a look at this language here. Okay, number one, we should realize that this language here is no longer regular. Okay, and by the way, there's a slight typo over here which I should fix. Okay, rather than larger than or equal to, just larger than. Strictly larger than. Okay. So this language here goes like this. It's a set comprehension. We are saying that we want to have the set of strings where we got 0 for as many times as we like, followed by hash, and also we want to have 1 followed by the same many times. Let's say if we can, it could be 0, 0, 0, hash, 1, 1, 1. It can be 0, 0, 0, 0, 4, maybe n times, followed by hash, and then 1, 1, 1, and also exactly n times. Okay? This language here is not regular, meaning that it's not possible for you to specify a recognizer either using a regular expression, DFA, NFA, or epsilon NFA. Just not possible. Just not possible. Okay? Non-regular, first of all. In order to prove it, I'll just mention the term. Remember, if you have heard about something called pumping lemma in 2001, maybe you have, that's what you got to use. But don't worry, we're not going to review that in this course, right? That'll be too much for theory, okay? But for those of you who might be interested, if you want to somehow prove about the language being not regular, you got to somehow use a pumping lemma, maybe pigeonhole principle a little bit, but let's not get there for this course. Now, regular cannot be specified, cannot be expressed, or recognized by any regular expression, NFA, epsilon NFA, or DFA. Just not possible. Okay? And this is the grammar. This is so-called a context-free grammar. Let's review the terms. This is what we call a context-free grammar. Oh, sorry. Context-free grammar. Context-free in the sense that we are only trying to look at the pattern of how the strings are being combined together in a recursive way, rather than trying to see whether there's any semantic analysis that can be done. We don't do that, okay? Context-free is opposed to context-sensitive. Focus only on the recursive pattern of the strings. On the other hand, no semantic analysis is done. Okay, we'll see a little bit more about the second point once we get to the case study, which we'll do after the reading week. But no semantic analysis is done. Okay, that's also important. Context-free. Okay, that's the first point. And then let's talk about the different terms. Let's start with the left-hand side. The left-hand side here, you can see A and B. So these are called the non-terminals. Meaning that whenever you got A or B somehow somewhere in your string, that means your string is incomplete. You should still do more derivation. It's not terminating. Or we call it the variables. On the other hand, anything other than non-terminals will be terminals. In this case, it would be, for example, you can see the 0 here, the 1 here, and also the hash over here, right? So these are called the terminals. Okay, this one here, and this one here. So these are the terminals, like a base cases in some way. Or tokens. This is the point I would like to emphasize. Even though zeros and one look like a character to you, I agree. But somehow to put more accurately in our context, think about when we actually pass the scanner, it's going to give us things like a 0, 0, 0, and then 1, 1, 1, a sequence of token. The token 1, token 2, token 3, and then followed by maybe a hash, etc. Right? That's more like a tokens rather than characters. They look like characters, but in our context, they're like a sequence of tokens. Okay, just to get it clarified. Okay, so we got terminals, we got non-terminals. I'll just say a little bit more. Non-terminals are the recursive cases. Oh, you know what? Let me not say that just yet. Okay, I'll get there a little bit later. Okay, non-terminals, terminals, and the very left, the top left corner over here. So this A here has a special name. It's called a start variable. Okay, I'll try to put it here. Oh, sorry. That one is a start variable. Meaning that if you want to do any derivation for your string to see if that can satisfy this particular grammar, you should start with the start variable. Okay, the top left corner. And then for each one of each line, you will see that, for example, A arrow 0A1. So this one here is called a production rule. But there are two kinds of production rule. That's really about the base case versus recursive case. Let me explain that. Okay, let me write it down separately. For example, if I have A produces 0A1 versus if I say B here produces hash. These two are both production rule. However, if you look at the right-hand side, this part over here is a mix of terminals and non-terminals. Because you can see that terminals, non-terminals. It's a mix. That means further derivation should be done. Recursive case. So this one tells you that this particular production rule is a recursive case. The whole thing is recursive. Meaning that more derivation are expected. More derivation steps expected. On the other hand, if you look at this one over here, B produces hash. This is like an extreme case. There's only one token there, and that token is exactly just hash, like a non-terminal. So this one here is non-terminals only. Beg your pardon, terminals only. And this one here is the base case. terminals only. Meaning that once you use this production rule, the result is going to be such that you don't need any further derivation, right? Let's just keep these two kind of production rules in mind. And once we go over the example, we're going to see that. All right, guys, if you don't mind, just let me take 1 more minute, right? I'm not going to miss you for 1 week, but just make sure you kind of check your e-class announcement. I'm going to release assignment number 2 on the coming Monday. I'm also going to, throughout the reading week, I'll send you maybe some guides about programming test, and also give you some, just keep you posted about what you should really watch out for the study. But do watch out for the semester calendar after the reading week. Things are going to be much more intensive, all right? So really try to review the slides on the math background, and also go over the Antler 4 tutorial video very carefully, and also keep up with the lectures, all right? I'll also announce some office hour as well during the reading week. All right, enjoy your study week. I'll see you in a week. Take care.